we're live. Okay, all right. Now, number one, in this question, the methyl group is represented by an Me. Triethylamine, that guy, reacts with boron trifluoride to form a compound of formula Me3N.BF3. Okay, how may this reaction be written in terms of the shapes of the reactants and products? Now, first of all, what shape will this guy have? Me3. Oh, I shouldn't do it like that, should I? What shape will this have, anyone? Anyone know the shape of this guy? Me. Because there's a lone pair on the nitrogen, it's going to be one of these. Let me get a nice color. It's going to be this shape, or this shape, or this shape, or this shape. So that doesn't help us. They're all the same shape. What shape is BF3, though? BF3, well, BF3 has 3 electron pairs, so this is trigonal planar. Okay, so which one's the trigonal planar? This one? No. So the answer is not B. This one? No. So already the answer is either A or C. Now, when they join together, the nitrogen here donates its electrons to the boron there. And therefore, around the nitrogen, there are 4 electron pairs. And around the boron, there will be 4 electron pairs as well. So you're going to get tetrahedral and tetrahedral. Which ones show that? Let me make this a bit bigger. Which ones show tetrahedral, tetrahedral? Not this one. This one, no, because this is square planar, so no. This is tetrahedral. This is tetrahedral, so yes. And this is good, but there's an X there, so the answer must be C. Okay, so the answer is 1C. Any questions about that one? Please tell me quickly while I grab the next question. If there is a question, let me know, Very, very quickly. All right, because I've got to grab the next question. All right. I can't see any of you now because I'm doing some clipping. Close that. New there. Okay, and we're going to collect that one. Okay, right. I'm assuming no one's asking anything. Get rid of this rubbish, and we'll do the second one. Guys, it's nice if you ask questions though, seriously, because otherwise I don't know what you're doing. Oh God, crying out loud! Give me a break! He just shouted right into my ear. Bloody hell, that scared the life out of me. It's like a ghost. I don't even know who it is. Hold on, who is it? Who's speaking? Jesus. Why is it not A? Oh, you sausage, really? You think it might be A? Is that a butler? Hello? Say something, someone. Hello? It was a butler. First. All right, it was. All right, so that cry came right out of the speaker, right next to my ear. It scared the life out of me. Why is it not A? Oh, you sausage! So I've got to go back, have I? Let's put A back in. Yeah, you've got to speak quickly because otherwise, there it is. Let's have a look at A. Which one is A? A is not A. Why don't you think it's A? Amante, if it's not you. Abodley, why isn't it A? You can speak now. I've turned the speaker down.
I don't know why it's not A.
All right, then. Now stay on the microphone, dear. I'll explain why it's not A. Okay. So you good with that one? Abodley, yes.
Yes.
Are you watching? Can you see the screen?
Yes.
Yeah, this is because of the lone pair there. This is pyramidal. Okay, you're good pyramidal. You're good with this one. This is trigonal planar. You good with that?
Yes.
Okay, but when the lone pair on the nitrogen bonds to the bromine and bonds to the boron, how many electron pairs are around the boron?
When what?
When the lone pair from the nitrogen, let me draw it over here. There's the nitrogen. When the lone pair from the nitrogen here donates to the boron, how many electron directions are around the boron now?
4.
4. So what shape must it be about around the boron now?
Tetrahedral.
And this shape here, can you see my drawing? That shape isn't
Yeah.
a tetrahedral. That's trying to show a square plane. Trying to show a trigonal planar.
Oh,
Does
okay.
that make sense? So this one here shows tetrahedral on the top half, tetrahedral on the bottom half. Does that make sense?
Yeah, it does.
So you're cool.
Yeah. Thank you.
Excellent. All right, no problem. Let's do that in future, guys. When you want to ask a question, could you put your microphones on? Because normally I accept typing only, but it takes so long to get that done. So this is number 2. The density of ice is 1 gram per centimeter cubed. What's the volume of steam produced when 1 centimeter cubed of ice is heated to 323 C at a pressure of 1 atmosphere? Okay, 1 mole of whatever occupies that. Now, the density of ice is this. So 1 centimeter cubed. So volume when 1 centimeter cubed of ice is heated to this at 1 atmosphere. All right, 1 mole of gas occupies 24 at that. Okay, now let's have a look at this. Where are we? So if I have, let's have a look at this. I'm going to use obviously gas laws here. So P1 V1 over T1 equals P2 V2 over T2. Okay, so the density of ice. So at RTP, yes, at RTP, the pressure is 101. The volume is of steam produced when 1 centimeter cubed of ice is heated. Okay, so 1 centimeter cubed of ice, so I've messed this up overnight, but 1 centimeter cubed of ice is 1 gram of ice, yes? Now, number of moles of ice, therefore, is 1 over 18, isn't it? Oh, that's not right. I put that in the wrong way around. So the number of moles of ice we're using, number of moles of water, I should say, is 1 over 18. Okay. Now, let's do 1 mole. Okay, so 101 pressure times 24, okay, divided by T1, and T1 is room temperature and pressure, which is 298. Okay, equals P2. All right, so what's the volume when it's heated to that? P2, the pressure doesn't change, so it's 101 times V2 over T2. Where's T2? T2 is 596K. Okay, so does that make sense? If I had, now I'm messing this up a bit because I think I'm rushing a bit. Let's have a look at this nice orange pen. All right, now what's this? This is 1 mole of water. Okay, and if we use 1 mole of water, the pressure 101 kilopascals, times the volume of 1 mole of water, which is 24, divided by room temperature. Oh, Basadi's here. Divided by room temperature, which is 298. Okay, so this is all 1 mole of water at RTP. Okay, that equals, well, the pressure doesn't change up here, so it's 101, times the new volume divided by 596, the new temperature. Okay, so I'm going to take 1 mole of water at RTP, okay, and I'm going to see what the volume is at 596K. Okay, this is 298K, and I'm going to see what the volume of 1 mole of water is at 596K. So these 101s are going to cancel out. V2 is equal to 24 times 596 divided by 298. Okay, this is for 1 mole. Okay, but 1 centimeter cubed of water is 1 gram of water, which is 1 over 18. It's an 18th of a mole. So the volume of this should be, well, this is the volume for 1 mole of 596. So I times this by an 18th to get what it would be for an 18th of a mole. All right, now, obviously I'm going to get my calculator out. I don't know if you can see my calculator. There it is, but you can't see it, I don't think. So 24 times 596 divided by 298 equals that, divided by 18 is equal to that. And I get 2.67 decimeters cubed. Anyone want to argue with that one? If you don't understand me, please moan. Don't just to take my word for these things, eh? There's no point in having these unless you go away satisfied. So please, do you understand what I did there? And you can put your microphone on, no problem. Oh, nice cup of tea. Anyone? I'm like, who's this? This is Wada. This is yeah.
Yeah. So, okay, you solve for V2 and then you're multiplying it by 1 over 8,
18.
which is the number of moles, 1 over 18, sorry,
Yeah.
which is the number of moles of the water.
Yeah. Do you want me to do it again, dear?
Okay, no, I'm fine, thank you.
All right. Now, look, these things aren't easy, but this is quite a tricky one. So what I did, let me start again, okay? I had to find out what the volume of water would be at 596 K. How much water? 1 centimeter cubed of ice. What would if I got 1 centimeter cubed of ice and I heated it up to 323 degrees centigrade, what would the volume be? If Belahing wants me to do it again, and I have no problem with that. There's no point in these things. Oh, Ahmad's here. There's no point in these things if we don't come away better. Is that clear, all of you? So honestly, if we spend an hour and a half on one question, I have no problem with that at all. All right, because we're here to learn, seriously, and we got to be patient with each other. All right, so if you understand something and I go through it, go away and get a cup of tea and come back later. All right, so I have 1 centimeter cubed of ice. Okay, that's a horrible thickness, isn't it? I have 1 centimeter cubed of ice. All right, now using the density 1 centimeter cubed of ice is equal to 1 gram of ice. Would we get that, Ipelching? Do you get that bit? Okay. Are we good with that? Ipelching? Are we okay? I'm going to continue until you do something anyway. So this, first of all, 1 centimeter cubed of ice is 1 gram of ice. I can't really do anything with a volume of ice, and that's why they give us the density. So if you remember, density is mass over volume, yeah, and therefore mass is equal to density times volume. Density is 1 times the volume is 1 equals 1. So 1 centimeter cubed of ice has a mass of 1 gram of ice. How many moles is that? Well, number of moles of water is 1 divided by this 1 here, divided by the relative molecular mass of water, which is 18. So they're giving me, they want to know the volume of 1 mole of water they want to know the volume of 1/18 of a mole of water at 598 K, which is 323 degrees C. Okay, now the pressure is constant. Okay, but let's pretend I have 1 mole of water. How many grams is 1 mole of water? It's 18 grams. Let's pretend I have 18 grams of water. And I'm going to use one of the gas equations, P1V1 over T1 is equal to P2V2 over T2. Okay, I could use PV equals nRT, but I'm deciding to use a simpler version, this one. So 1 mole of water, well, at 101, which is atmospheric pressure, the volume of 1 mole of water is, where is it? Is 24 decimeters cubed. So, and at T1 is at 298K. So I know these things. I know that the volume is 24 at 1 atmosphere at 298K. That's my first situation. If I heat this up under the same pressure, so the pressure is 101, the new volume will be V2, okay, divided by the new temperature, which is 596. Now, if I solve for V2 here, if I solve for V2, and let me solve for V2, well, first of all, I didn't do this before, did I? What I did last time is I cancelled things out and I did weird stuff. So I'm not going to bother with this because this is going to cancel with this. But if I solve for V2, V2 is going to equal 24 times 596 divided by 298. Okay, let me push that up. This is solving for V2. And let me do that. I'm going to get my calculator out again. If I can find it. It's down here somewhere. All right. Actually, I've got a brand new calculator next to me. Right. So this is 24 times 596 equals that divided by 298. So the volume is 48 decimeters cubed. This is the volume of water. Okay, but this is the volume for 1 mole of water equals 1. If I have 1 mole of water, it will have a volume of 48. Okay, I hope that makes sense. So it's going to have a volume of 48, 1 mole. But they didn't give me 1 mole, they gave me an 1/18 of a mole. So the volume of an 1/18 of a mole is going to be 48. Oops, what happened there? Is going to be 48 divided by 18, which apparently is 2.67 decimeters cubed. Does that make sense, Ipelachi? Yeah, look, you know what, guys? These aren't going to come easy to you. You just got to practice them. I tell you, try and do what I've done and try and follow it through. Okay? It's not easy at all, dear. Seriously. All right. Now, I'm going to do number 3 now. So I've left you. I can't see anyone now. So I've got to turn that on. And that goes there. All right. So number 3. I'm looking for number 3 now. And number 3 doesn't look too hard. It looks like a nice, easy one, to be honest with you. But you never know your luck, do you, in the big city? Okay, so number 3. I was hoping, as you all know, I was hoping that you would tell me which ones you wanted. But and then obviously someone said all of them. All right, so we'll do all of them. I have no problem doing all of them, don't worry. Whoopsie daisy. Oh, that's gone weird. Right, now get rid of this. Get rid of this rubbish. Okay. Oof. This question isn't too hard, so this shouldn't be bad. Images, my device, 333, this one. Okay. So which pair of elements have bonds of the same type between their atoms in the solid state? So between atoms, between an aluminium and an aluminium, what's the bonding between an aluminium and an aluminium? Anyone want to help me there? Anyone know what the bonding between an aluminium and an aluminium is? Hold on, there we are. Anyone? Anyone at all? Anyone's fine. I'll help you if you don't get it. Between an aluminium and an aluminium, it's metallic bonding, isn't it? All right. Between a phosphorus atom and a phosphorus, it's covalent bonding. So A is not the right answer. Between a chlorine and a chlorine, it's covalent. But between an argon and an argon, well, there's no bonds there, is there? So the only bonding between an argon and an argon is a van der Waals force. Okay? Between magnesium atoms and magnesium atoms, it's metallic. Between silicon and silicon, it's covalent. So that's not C and it's not B. Between sulfur, it's covalent. And between chlorine and chlorine, it's covalent. So the answer must be D. Anyone have a problem with that? If you do, give me a shout quickly if you can. I'm getting rid of all this rubbish from the previous question. So I hope we're okay with that one. All right, let's get this new program that they use, Microsoft whatever it is. It used to be. You have a problem, Basadi. What's the problem? You give me a chance to clean up. Yes, Basadi. What's the problem? Oh, there it is. There's stuff down there. Yes, Basadi. You can put the microphone on there. Anyone? Basadi just says she has a problem, but we'll never know what the problem is. Zali, what's the problem, dear? Oh, there's another bit, isn't there? Mm-hmm. It's okay. All right then, dear. All right. Now I'm trying to. Oh, there we go. I'm trying to increase the size again. There we are. 108. All right. So let's do the next one. If any of you have got a problem, you got to ask. Okay. As we say, this is why we're here today. No point pretending you understand stuff if you don't. All right. The next one is about the ideal gases, and this is this one. All right. So let's do this. Let's include this one. My device. This is 444. Okay, this is the question 4. Which diagram correctly describes the behavior of fixed mass of an ideal gas? T is measured in Kelvin. Okay. Now, I remember drawing diagrams in class on this. Okay, so what have we got? We've got a fixed volume. Okay, and we've got a plunger. Well, the volume can change, can't it? Okay, and the pressure. This is the volume of the gas. All right, and how far the plunger is pressed in is the pressure of the gas. So if I increase the pressure, okay, what will the volume do? So pressure, if the pressure goes up, the volume will go down. Okay, let's have a look at the first one. Well, this says if the pressure is high, the volume is also, oh, the volume is low. Okay, so if I increase the pressure up here, all right, as I'm doing in this way, the volume will get smaller and smaller and smaller. Now, that on the face of it doesn't look like a bad option. Can anyone tell me why that isn't the answer, though? Why A is wrong there? If I increase the pressure, won't the volume decrease? And again, you can put the microphone on, that's no problem. Why is A not right? Anyone? Anyone? No one? No one wants to say anything? Right. The volume is proportional to 1 over pressure. So if we plotted volume against 1 over pressure, we would get a straight line graph. Okay? But that's not what the graph says. It's P against V. So if I plotted volume against pressure, at very low volumes, you would have at very low pressures, you would have a high volume. And at very high pressures, you would have a very low volume. So the graph would actually look like this, but it would never come to zero. Okay, so it's not going to be a straight line as this says. Okay, so it looks kind of good, but it's not good. Okay, are we okay with A? So the answer is not A. Okay. B, it says PV against P is it does this one at constant temperature. Right, PV, if you remember, P1 V1 is equal to P2 V2. All right, if you remember that. So if I increase the pressure, all right, if the pressure goes up, the volume goes down, so that P1 V1 is a constant. So if I increase the pressure, it doesn't matter. PV is always a constant. So PV against P is a straight line graph for a noble gas or an ideal gas. Does that make sense? I'm just going to have to get used to no one speaking here. PV, if I increase PV again, if I increase volume, PV will also be a constant. Because, yeah, it does. I hope it makes sense. Because if I increase V, PV is going to be a constant. Because if you increase V, P will decrease. PV is a constant. So that will be a straight line as well. Now, the last one is the one that the answer, obviously. If you have a volume of gas, okay, all right, under constant pressure, in other words, I can't push and pull this plunger, and I have a volume of it. And if I double the temperature, the volume will double. So we say V is proportional to T. If I double the temperature, the volume will double. And I get a proportionality graph between V and T. I get a straight line going through the origin. So this is the answer. Okay. Now, again, it's not an easy question. Okay. Right. Anyone want to argue with that while I'm digging around for the next question? Anyone?
Can you please answer? I have a question.
Oh, hold on. We got two at once. All right. I don't know who was first. Who's first?
It was me. Can you explain B and C again?
Okay. All right. Now, let's have a look. B and C. No problem. All right. So let me get you on. I can't see this. Is that about again? Right. Now, here we go. All right. Let's get rid of some of this rubbish. Now, basically, I think we did a lesson on ideal gases. I'm pretty sure we did. All right. And it's all to do with that rubbish. All right. Now, okay. What is PV? Let's have a look. Would you agree? And I think it was a booklet, but that's I can't remember who it was. Right, we've got a syringe here, okay, and there's a volume here. Let's say the volume is equal to 1 decimeter cubed, all right, and the pressure pushing this in is 1 atmosphere. I think you would agree. That's a nice simple system. And now I'm going to do it again, all right. And I'm going to double the pressure, and I'm going to push my gas in. So pressure is equal to 2 atmospheres now. And what's going to happen to the volume? Well, the volume is going to go to 1/2 a decimeter cubed. So was it about there or Amantha? I don't know who said that, but does that make sense? So far, so good.
Yes.
Excellent. All right. So what have we got in the first one? Well, we've got PV. P1V1. And what is P1V1? Well, P1 is 1 times 1. So PV is equal to 1 times 1. What have we got over here? Well, P2 times V2 is 2 times 1/2. So 2 times 1/2 is equal to 1. So from that, we say P1 V1 equals P2 V2. For an ideal gas, PV is constant. Okay. Now, about that, it's not. I can't take this gas over there and this gas over there. It's for the same gas. So if I start off with a gas, there's my gas in a box. Okay, I can't get another bottle of gas and say, "Oh, this is the same as this." It's what I do to the same gas. So if I look at this gas here, the one I'm pointing at here, and I work out PV, okay, and then I change the pressure on this, and I work out PV for the same mass of gas, PV will be constant if the gas is ideal. PV for an ideal gas is constant. Does that make sense? For the same mass. Now, there's another way we can look at it. PV equals nRT. Okay? Now, if the temperature is constant, this is a constant. R is a constant. Yes? Now, what's the only thing that makes PV change then? It's the number of moles of gas. Would you agree with that? N, the term N. So, the only thing that will change PV is if I change the number of moles of gas. Yes? But in this case, it says a fixed mass of gas. So, I'm keeping N constant as well. So PV is a constant for an ideal gas. Does that make sense, dear?
Yeah, it does.
Are you sure? You can't, don't just say yes because you want to be nice and stuff. So if I have PV for an ideal gas, yes, P1V2, and I increase P like they're doing here. If I go to P2, well, V2 will change. If I increase the pressure, the volume will decrease such that PV, P1V1 is equal to P2V2. And therefore PV will be a constant. PV against P is a constant. The same argument for this one. If I increase the volume, the pressure will decrease. If I make a gas bigger, the pressure in the gas will decrease. And so PV is a constant. Yes? Now, you may have seen this when we do PV against, what do? We do PV against P. All right, and we discuss about the ideal gases. So let me get rid of this rubbish here. Okay, and what you may have seen is these graphs. Okay, they do this. They go down and up. This is for an ideal gas. This is PV against P. And for an ideal gas, PV is a constant. So this is the dotted line. But for a real gas, this happens. Real gas. And if this deviation from ideality is caused by intermolecular forces. Okay, an ideal gas doesn't have any intermolecular forces, so it doesn't dip. But a real gas does have. All right, but this particular question is about an ideal gas. Does this make sense? Now, if it doesn't make sense, and all of you agree it doesn't make sense, we need to do more work on this topic. Okay, but if you're okay, we'll leave it for now. I don't know. What's the consensus? Anyone can answer. You're okay now. Well, I hope you are, dear. I think we need to do more work on it. You know what? I think well, we're doing organic now, obviously, but I think next week maybe I'll have to try and try and put some in the homework. Okay, all right. I think we do need more work on this. Anyway, but can you see why this particular answer is D? Okay, because if I increase the temperature, what's going to happen to the volume? The volume is going to go up because the gas is going to increase in volume. Now, V is proportional to T. What does V is proportional to T mean? Now, this is a strong statement. Okay, it doesn't just mean if you increase T, V goes up. It doesn't mean that. It means if you double T, V will double. If you halve T, V will halve. Okay, but T must be in Kelvin. It can't be in centimeter. It can't be in degrees C. So if I plot V against T, it must go through the origin, and it must be a straight line. That's what proportionality means. If we draw V against T, it must go through the origin, and it must be a straight line. Okay, so this question looks harder than it actually is. The answer is looking at it in the face. It's obviously this one. It must be D. Okay, does that kind of make sense? I understand you're not very confident on this, and we should look at this again. But are we okay for now, for today? Can we move on with today? I understand you're not great at this, though, honestly. And that's why we're here, eh? We've got to figure these out. All right. But you know what? You're all good for coming, so I can't complain, can I? Right, rubber this up, rubbish out. Oh, I've got a nice cup of tea going. You know what? It's tea, but I think it's soy milk, and it's actually quite nice. I never thought I'd like it, but it's quite nice. Right, let's have a look at this, my device. And now we're doing number 5, I think. Oh, didn't I say that? Number 5. Oh, same one, not that one. All right, so this one, we're nearly there, don't worry. This one's number 5. Oops. Yeah. Okay, my device. Number 5. Oh, there it is. Okay, so this is number 5. All right. The question is, for which enthalpy change corresponds to the atomization of iodine? Okay, so first of all, you've got to know what atomization means. Okay, and it's basically the formation. Oh, that's not a nice pen at all. Let's do this color. It's the formation of atoms from the elements in its standard state at room temperature and pressure. All right. Now, how many moles of atoms do you think we have to make for it to be an enthalpy change of atomization? How many moles of atoms? Exactly. So it's 1 mole of atoms. 1 mole of atoms. So this one could be right, and this one could be right. But this is wrong, and this is wrong because it's got 2 there. Okay. Now, which is iodine's standard state? Well, iodine, whether you like it or not, is I2. That's its standard state. Its state at standard state is a solid. Okay, is this. So I've got to make 1 mole of iodine atoms. So I've got to start off with half a mole of iodine molecules. Now, I don't want the atoms in a solid because they wouldn't be atoms then, they'd all be molecules. All right, so I want them in a gas. So the answer is B. Does that make sense? I hope that makes sense. I'm going to go to the next one. If you want to argue with that, that's no problem. All right, now we click that on. Okay, please shout if you want to shout. That's no problem at all.
Sir, what's the difference between enthalpy change of atomization and of formation?
Oh, okay. Right, now formation is, well, first of all, let me get rid of this. It's a good question. And what I'm doing, I'm going to close that down. Right, let me get rid of some of this rubbish. Okay. Now, formation. Okay, let's have a look at the enthalpy changes. All right. So, first of all, let's do atomization. 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 Now, when we're going to do atomization, we get 1 mole of gaseous atoms. Okay. What do we get them from? From the element in its standard state. Okay, so this is this one. What's formation? Now, believe it or not, formation always refers to compounds. Okay, all right. Now it's forming 1 mole of compound from its elements. Under standard conditions. All right. Now let's pick something. Let's pick randomly. Let's pick methanol. Methanol is CH3OH. Okay, and let's do the formation of methanol. All right, now 1 mole of methanol, so I've got to leave it like that. It's got to be one. Methanol is a liquid at standard state, so I've got to make that. So this is how I do it. I kind of work backwards. So there, what does it come from? It comes from carbon. Carbon is a solid under standard conditions. It comes from hydrogen. Hydrogen is a gas under standard conditions. And it comes from oxygen. Oxygen is an O2 molecule gas under standard conditions. So now I've got to balance this equation. But the interesting thing about this, let me get a nice color here. Interesting about this is this number here must remain 1. So carbons are good. Hydrogens, I need 2 of these. Oxygens, I only need 1 oxygen there. So we need a half of this. Okay, and now this is delta H formation. It's the formation of 1 mole of compound, and atomization is the formation of 1 mole of gaseous atoms. Okay, now atomization refers to elements, so it's got to be gaseous atoms from the elements in its standard state. But the formation refers to a compound from its elements under standard state. Let's try and make sodium. There's sodium. Sodium is a solid under standard conditions. Yeah. And how do I make sodium from its elements? Well, sodium from its elements is sodium, isn't it? And that's why the heat of formation of elements, by definition, must be 0. Because you're starting with elements and you're finishing with elements. Does that make any sense at all, dear? Are you okay with that?
Yes, it makes sense.
Are you sure? Don't forget, there's no point lying to each other, right? Because you've made the effort to come here. So are we all good then? We're all good there.
Yeah, we're good.
Excellent stuff. All right, let's get rid of this one. We haven't done, obviously, if we're going to go nice and slow like this, we're not going to do many questions, but that's okay. You know what? That's okay. I have no problem with that. If one of us learns one thing, it's worth it. All right. Okay, so let me get rid of this rubbish. Okay, oops, and get rid of this one. This new, as I say, whiteboard is a real pain. The old whiteboard was much nicer, much quicker to use. And for some reason, Microsoft updated it to this one, which is a pain to say the least. All right, now this is another enthalpy one. I don't know how good your enthalpy is, but let's have a look. Let me try and do it. Titanium occurs naturally in the mineral state of TiO2. One possible method for the extraction is to reduce the rutile by heating with carbon. There we go. Standard enthalpy changes are that, and that. What is the standard enthalpy change for this reaction? Now, this is how I do them, and I'm sure you do them the same way. I construct what's called a Hess's triangle. Okay, triangle. Okay, this is the only way I can do it. Okay, so I do titanium oxide. Now, I wouldn't do this in the exam. I wouldn't write down this equation because I'd use the paper itself. Okay, but I do this. Now, what we've got to do is we've got to find this one, delta HR. That's the one I need, okay? It's the delta H of the reaction. And it's given me the formation of titanium and that and that and that. Okay, so now it's given me formation information. So down here, I'm going to start with my elements, titanium and carbon and oxygen, okay? And therefore, from here to here is the formation of titanium oxide, and from here to here is the formation of 2 carbon monoxides. So I'm going to call this transformation delta H1 and this transformation delta H2. Now, by Hess's law, from here to here must be, in other words, from here to here must be the same as from here to here to here. Does that make sense? Do you all understand Hess's law? Because what I'm trying to say here is it doesn't matter how you get there. If you start at the same place and finish at the same place, it's the same energy. Does that make sense? I hope it does. Well done, Monet. Right, so using this, delta HR, the one I need is this direction to there. So this direction is minus delta H1, and this direction is plus delta H2. Okay, what is delta H2? It is the formation of 2 carbon monoxides, and carbon monoxide is minus 101. So minus 110, sorry. That's all of this rubbish is delta H2. 2 formations of carbon monoxide minus the formation of 1 titanium oxide. And the formation of 1 titanium oxide is minus 940. All right, and I'm going to use a calculator there. Maybe you're quicker than me. All right, I get 110 times 2 equals that. That's going to be minus 220. So I have minus 2, whoops, it is, what's happening with my calculator? Minus 220 plus 940. So I get 720 because this is a negative and this is a negative. So I end up with plus 720 kilojoules per mole. Okay, anyone want to argue with that? If you do, please give me a shout. I'm looking for the next question. Are we good? All right, if you want to argue, go for it. Honestly, there's no time like the present for arguing. Okay, next one. Bazadi normally wants to argue. I don't know why she's not arguing today. All right, there we go. And let's get rid of this. The reason this is a pain, the old one, it allowed me to scrub the entire screen with one button. Now I have to scrub it like this. It's a real pain. I don't know why they changed that. It's just awful. Anyway, let's add this one. Images, and this is 777. There we are. This is a lovely question. I'm sure you got this one right. Are we okay with this one? Maybe we can ignore this one. Or if you want me to just do it, let's go for it. So are we okay for this? You would argue, but I just need to process. Well, the thing is, we're okay. What is okay? Are we all okay? I don't know what the answer is, but are we all okay? Okay, let's ignore that one, even though I just copied it. All right, let's do the next one. Number 8. That's easy as well. It's which element is expected to show the greatest tendency to form covalent compounds, and that's aluminium. We did that in class. Number 9. This one may be a bit awkward, so let's do this one. Number 9. It's about some organic-y thing. All right, so this is number 9, 9999. Save that and close that down. Get rid of this and add this. God, it's such a pain. It used to be so easy importing images, but now it isn't. All right, this one, chloroethene, is that. And the mono is a monomer of PVC. What is the CCC bond angles in the polymeric chain? Okay, now if you do the polymer of PVC, it's this. It's loads of carbons in a row, loads, and it's got CHs. And there's the ends of the polymer, and there's the other end. And H at the top here, and Cl. H and H, H and Cl. H and H, H and Cl. Now, guys, this is straightforward, I think. How many bonding directions are around this carbon? Well, there are 4 electron directions. Therefore, we know it is sp3 hybridized. And therefore, we know it must be tetrahedral. And if it's tetrahedral, it must have all of them, because they're all 4. It must be 109.5. So the answer is A. Piece of cake. All right. Anyone want to argue? Please argue now while I'm getting the next one. If I don't hear from you, I'm assuming no one's going to argue. All right. So we're on number 10 now. 10. Okay. Get rid of that. Get rid of this. Get rid of this rubbish. Okay, number 10. I don't know. What is this? Yeah, I don't know if this is a hard one or an easy one. We'll see. Right, number 10. Device. Now, is anyone got to go? Because I know some of you have supper and stuff. Should we? Well, hold on. Someone's there. Yeah. Oh, Mosa wants to join. Mosa, why are you joining now? We're just about to quit. Right. Which quantity would best indicate the relative strength of the hydrogen bonds between molecules? Okay. Does anyone want to answer this one? This is the last one we'll do then, all right? Because it's already 6:10. You were doing well now. It's up to you. All right. Priorities. Yes, I can tell you. All right. Over school. Yes, dear. We understand. We've seen your grades. Whoa! Right. Now, what do we get here? The relative strength. This is the last one we'll do. The relative strengths of the hydrogen bond between the molecules in liquid hydrogen halides. Okay. Now, right. Bond dissociation energy. So let's have a look. You've got something here. Hydrogen halide. All right, and there's a hydrogen halide. Let's do it HCl. Let's do it differently. I think you guys just messed this up for not thinking, really. All right, what does bond dissociation energy mean? What bond are we breaking? What bond are we breaking? Quick, because I want to go. You want to go? Someone just say on the microphone. What bond are we breaking if we bond dissociate? I'll do it then, shall I? If we dissociate, we break this bond. Yes? Exactly, Basari. It's the covalent, and we end up with H and Cl. Do we want this? Is this the one we're looking at? For the relative strength of hydrogen bonding. Hydrogen bonding talks about intermolecular. Bond dissociation energy talks about breaking covalent bonds. Yes? So it's not that one, is it? A is wrong. Enthalpy change of solution. The hell's that got to do with hydrogen bonding between molecules? Enthalpy change of formation. What the hell's that got to do? Enthalpy change of vaporization. Yes, because if you have a liquid, this is a liquid. All right, and these balls are HCl molecules. This is liquid HCl, and it does say liquid HCl. How much energy is it going to take to vaporize this to get one of these out of the vapor? If I vaporize one of these HCl molecules, What bond am I breaking within the mixture? Am I breaking the covalent bonds or am I breaking the intermolecular bonds? I'm waiting for someone to type it before we can say goodnight. Mosa, you do something useful with yourself. What would you do? What are we breaking if I vaporize one of these molecules? Anytime. Has everyone gone? Yes, we're breaking intermolecular. All right. It's intermolecular. Exactly. Well done, Basadi. Well done, well done. And so what bond is that? What's intermolecular? Hydrogen bonds are intermolecular. Yes, these are intermolecular. So it must be D, mustn't it? If we vaporize something, it gives us an idea about the strength of the hydrogen bonding. So are we okay with that? Can we? Oh, what am I playing? Why? Go on the microphone, Amantle, quickly, because I don't want to. Quickly, dear.
No, what I'm saying is I don't think I understand what the question's even asking.
All right. It says, how can you test the strength of the hydrogen bonds between the molecules in liquid hydrogen halides? Okay. So you've got HF molecule and an HF molecule, and you are comparing that with a HCl molecule and another HCl molecule. Yes? Now, what's the hydrogen bonding? The hydrogen bonding is the bonding between the molecules, isn't it? Yes? So the first one, bond dissociation energy, doesn't talk about the bond between the molecules. It talks about the bond within the molecule. So A is wrong. Enthalpy change of solution doesn't mean anything because there's no solution here. Enthalpy change of formation, that doesn't tell you anything about the hydrogen bonds. But if I asked you, how would you test the strength of the intermolecular bonds? One of the things you would say is, oh, I would find out the vaporization, the enthalpy change of vaporization, because the enthalpy change of vaporization will increase the stronger the hydrogen bonds. In other words, it will take me more energy to vaporize something if the hydrogen bonds are stronger, and it will take me less energy to vaporize something if the hydrogen bonds are weaker. Are we good? Amantle says she's okay now. Okay, but it's a good question. All right, guys, well done. Unfortunately, we only got to 10. We should do, maybe we should do, next time I'll have all the questions cut and paste already. Let me stop the sharing for now.